at that end, on the right end, it's a short circuit. What is the meaning of short circuit? The voltage is 0. So if we call this V plus, what comment can we make about the total voltage is V plus V minus. That must be equal to, what is that? If this, the forward and backward going waves here are V plus and V minus, right? What is the total voltage at that end? It's V plus V minus, and that must be equal to 0, right? Which basically means that, what is V minus? Minus V plus. Correct? So, alright, so if this forward going wave is V plus, what comment can you make about the forward going voltage wave there? The voltage on the right is V plus, it's going this way. So what must be here at the left end must be an advanced version. So that basically is V plus e to the s times t. And likewise, the voltage the backward going wave must be minus V plus e to the minus s times t. Correct? So what is the total voltage at the left end? What is the total voltage at the left end? It's V plus times e to the s times Td minus e to the minus s times Td. And what is the total current? The forward wave is associated with the current flowing in the, going into the line, which is V plus e to the s Td by Z naught, and the backward wave is associated with the current which is flowing in this direction. So the total current is simply the forward current minus the backward current. So that's basically V plus by Z naught times e to the s times Td plus e to the minus s times. Correct? So therefore, what is the input impedance? It's e to the minus e to the minus s times Td by and this is nothing but times Z naught. This is Z naught tan hyperbolic s times. Sanity check. Pardon? At Td equal to, oh well, yeah, sure, okay, fine, but Td is okay, that's one thing. If Td is not equal to 0, what must be the DC impedance looking in? What must be the DC impedance looking in? It's a short circuit, right? Okay, it's a short circuit. We have done it through a cable, but hopefully the cable basically does not mess up the DC shock. Correct? And so as s tends to 0, clearly the tan hyperbolic s times Td goes to 0. So fortunately, we still have a short circuit even though we have an expensive cable. Does that make sense? All right. And so as frequency becomes higher, as s starts to increase from 0, what do you see? How does it look like? At low frequency, At DC, of course, it's a short. At low frequency, what does it look like? Or, okay, so, well, I would say put S equal to j omega. This is Z naught. So, this is e to the j omega T d minus e to the minus j omega T d by which is Z naught. What is the numerator? J sine omega T d by cos omega t. So, if you plot the magnitude of the impedance, you can see that at DC it is 0, right. So, Z in of j omega that is at DC it is 0. As omega increases, what do you see? How does it go? Well, it goes as, yeah, I mean for small omega, what do you see? Well, it's Z naught times much smaller than 1. Z in of j omega is approximately j Z naught T d times all right. So, it looks and how does this, what does this remind you of? This is an inductance. So, why does this make intuitive sense? Huh? Yeah, inductance is a short, but I am asking you what is the value of that inductance? What is the value of that inductance? Z naught times T d, correct? The question is, why does this Z naught times T d, does it make any sense, or does it, or you say, well, what can I say, it comes out of the math. Very good. Z naught, remember what is Z naught? It's square root of L by C, where L and C are per length, unit length values. And what is T d? T d is nothing but length by velocity, which is basically, velocity is nothing but square root correct. So, Z naught times T d therefore is nothing but L times C times square root of L C times x, which is therefore L times x, the C goes away. So, this is nothing but, I mean, does it make intuitive sense or no, right? So, you have this LC where were we? Yeah, network, right? Each one of these inductances is some L delta x. You have a transmission line, right? You are shorting the output and you are looking at the impedance at this end at low frequency. At low frequency, what is the current flowing through all those infinitesimal capacitors? 0. So, what you essentially look at is, you are looking at the total inductance, right. So, basically, so this is the total inductance of the line. alright. And so that's one thing to bear in mind. The next thing is what? If I plot this Z magnitude of the impedance, well, at low frequency it does this. As the frequency starts getting higher and higher, what happens? When omega times Td becomes pi by 2. So, that basically is omega equals pi by 2d, or this is nothing but 2 pi f equals pi over 2d. F is nothing but 1 over 4 times Td, right. What happens? Well, it goes, the magnitude of the impedance goes to infinity, okay, and at 1 over 2 times Td, it comes back to 0 and then again goes up. All right. So, what is the moral of the story? Well, we were expecting a short circuit, correct? And we naively said, oh, we will take a cable and then short the other ends of the cable. And voila, I mean, you know, at DC, of course, it's a short, right? But it does all sorts of wild things, right? Okay. At if the input frequency is, you know, some magic value, which is, you know, as you can see, an odd multiple of 1 over 4 times Td, right, where Td is the length of the cable, then what was supposedly a short circuit can actually look like an open circuit, all right, okay. And between frequencies of 0 and 1 over 4 Td, it can look like anything between a short and an open, okay. So, like all things in life, you know, right, things are more complicated than they seem, all right. So, you know, this whole notion of getting a short circuit is supposed to be zero impedance at all frequencies, right. So, like most things in a textbook, it doesn't exist, right, because, you know, the moment you put a two conductors with some finite length, right, the best you can do is, as you keep making the length shorter and shorter, what will happen? Well, the frequency at which this happens becomes higher and higher, but you can't escape from that slope. The best thing you can do is you can get a small inductance, correct, all right. Now, I am going to quickly take a few minutes and then finish off the open circuit stuff too. So, the bottom line therefore is that you know, the perfect short circuit does not exist. That's your take home message, all right. And if a perfect short circuit doesn't exist, what comment can you make about the open circuit? Well, a perfect open circuit doesn't exist, probably doesn't exist either, right. A perfect, I mean, in the best case, you can make, I mean, a short circuit to first order looks like an inductance, right. So, an open circuit to first order will look like a capacitor, right. So, let us quickly, so this is an open circuit. So, what is the definition of an open circuit? The current is 0. So, if this is V plus, the current flowing in corresponding to the forward wave is what? V plus by Z naught, and the current in the backward wave, this is V minus. So, V plus by Z naught minus V minus by Z naught, that is the total current flowing out of the transmission line. That must be 0, which basically means V minus equals V plus. right. So, this is basically V plus. Now, what must this forward wave be? This must be V plus e to the plus STD, right. And what must this be? V plus e to the minus STD. So, what is the, I am going to skip all the algebra. You should now be able to tell me what the impedance is. What is the impedance? Is Z naught times, what is the voltage? E to the STD plus e to the minus STD divided by STD minus STD, which is Z naught cot hyperbolic S times T, right, which is basically therefore Z naught open circuit of j omega therefore is Z naught by j Z naught cos omega TD divided by j sin omega. Correct? So, at low frequency, I mean sanity check at DC, well, it is an open circuit and fortunately it does indeed turn out to be infinity, correct. So, at frequencies which are small compared to, so for omega times TD much smaller than 1, the impedance is nothing but Z naught by j times omega TD, correct. So, this looks like a capacitance, and what is the capacitance? The capacitance TD over Z naught, and straightforward math will tell you that this is simply nothing but the total capacitance in the transmission line, and that makes intuitive sense because at low frequency the voltage drop across the inductors is, it is an open circuit. So, the voltage drop across the inductors is very small. So, the applied voltage appears across all the capacitors. So, the current that flows in is simply nothing but 1 over j omega C, where C corresponds to the total capacitance of the line, right. So, therefore, so the capacitance is TD over Z naught, total inductance is Z naught times, right. So, these are good relationships to know, all right. So, okay. So, now this is the theory. So, let us say you walk into a lab, right, and you see a cable which is 2 feet long, or let me make it 3 feet long, right. Now, you want to figure out whether a CMOS inverter will be able to drive this load, right. Okay. So, the question is how much capacitance does this cable have? This is a great interview question, right. here is a lab where you walk in, right? Your host in the company takes you into a lab, right? Shows you a cable. This says how much capacitance is there in this cable. And particularly because you've put down 4 internships in your on your CV, which right, at various impressive companies, right, doing things that only you can do in 2 months. All right. How will you figure it out? Pardon? So, well, the cultural part of the question is, what is Z0? You have done enough courses to know this. What is the standard impedance used? 50 ohms. Well, we got that out of the way. Right? We need to find TD. Okay. Well, 3 feet is approximately a meter. Right? So, that is 1 meter divided by velocity of light, right? And even if you didn't know the velocity of light in the medium, right? You know that it's going to be faster or slower than 3 into 10 power 8. Slower than 3 into 10 power 8. And do you have can you hazard a guess of what the dielectric constant is? Well, what is the dielectric constant of, I don't know, maybe glass or silicon dioxide? Well, it looks like glass in the middle. I mean, obviously, this inner conductor can't be floating in the floating inside the cable. There must be some mechanical medium which must be holding it in place, right? It turns out that 4 is a good number to use, right? Okay. So, what is the speed of light in the medium? The nice round number is 1.5 into 10 power 8 meters per second. So, this is how much? This 2/3 into 10 power minus 8, which is about 6.7 nanoseconds. Correct? I hope not made a mistake. Yeah. Alright. So, the capacitance therefore is 6.7 nanofarad divided by 50, which is 130. Does it make sense? Right? Okay. Which is why a 1 farad capacitance is a huge capacitance, right? So, this is like 1.5 foot long, 3 foot long cable, right? And it's got only a capacitance of only 100 picofarads or so, right? To get therefore, what do you call microfarads or nanofarads, or farads of capacitance, you better pack things very, very, very. What is the inductance? What is your estimate of the inductance? $50 times 6.7 nanohenries, which is 330. Right? So, if you short the ends of the cable and look at the other two terminals, and then at low frequencies it will look like an inductance of 330 nanohenries, If you open circuit the cable, it will look like a capacitance of value 130. Does it make sense, people? Okay, right.